let's look at parameterized surfaces. I'm using the CalcPlot 3D web applet, which is really helpful, and it's got a mode, so I cleared it out first using the clear thing, and then I went to select and select a parametric surface, or parametrized surface, same thing, okay? And so I actually am using the default, and I'll talk about the default, and then I'll do two other quick examples. So we'll look at this, and I just clicked this checkbox to actually make it active, and I want to talk about just the basic idea and why does this create a sphere, which is exactly what it does. So parameterized surfaces are like parameterized curves, but you put in two parameters, u and v, and for all those all the values of u and v in the region that you want, and often, not always, but often that's going to be like a rectangular region in uv, it's going to calculate x, y, and z based on these formulas. So one way to think about it, and a really good way to analyze it, is to think about it, break it down into curves, and that's what most pictures do. They'll show you something that's got a grid system, and that grid system is two families of curves that are what happens when you set u equals a constant and you vary v, or you set v as a constant and you vary u. For example, here, if you set v to be a constant, then notice that since z depends only on v, if v is a constant, then z is going to be a constant. Okay, and then this part, the 2 sine v in here, is going to be a constant, the same constant. So it's going to be like a radius times cosine of an angle, radius times sine of an angle. Okay, that's going to draw a circle in a certain constant z-plane. If, on the other hand, I set u as a constant and v as variable, then cosine u and sine u are constants, and then I've got something that is a different circle. This is going to be sine v in x and y and cosine v in z, and that's going to give me the meridian circles, or the longitude circles, on the sphere, which are the ones that go from North Pole to South Pole. Now, of course, this is, in some ways, it's very familiar because it's a simplification of something that in some ways is more powerful. If you let this 2 become one more variable, our radial variable, sometimes called rho, sometimes called r, then this is exactly spherical coordinates that describe all of three-dimensional space. So one way for this particular parametrized surface is you can think of it as we actually had something that we could describe a point in all of three-dimensional space, and then we just set one of those parameters to be a constant equal to 2. That's not true for a lot of parameterizations. It's not the best way to think of a lot of parameterizations. But your go-to thing is just to figure out what are those curves going to be? What are the u equals constant curves and what are the v equals constant curves? And that's something that shows up in a lot of uses of parameterized surfaces as well. So let me go ahead and change this to something much simpler here. U and v and u squared, excuse me, plus v squared. Okay, so now what have I got? I've got something, well, it's a little bit weird. I'm getting like, it looks like I'm getting sort of a quarter of something, maybe a quarter of like a bowl sort of shape. And of course I'm only getting a quarter because the parameter values here, they were only positive. And that's pretty standard for spherical, but let's just change this to like -1 to 1 and -1 to 1. Okay. Enter should do it. Yeah, there we go. Okay, so now, okay, it is a bowl, okay, and notice that the grid lines, if you look at it from the top, they're exactly just the usual xy plane grid lines, and that's because I'm using a very special parameterization here. It's called the graph parametrization. If my function z is known as a function of x and y, in particular, here it's z equals x squared plus y squared, then I can just set x to be u and y to be v, and z to be just that same function expressed in u and v. It's a very special case of parameterization. It works if your function was a graph to begin with. Notice the sphere, that would not have worked. It's not always the best way even if it is a graph, and we've seen that for parameterized curves as well. But if you want something where the grid system looks from the top down, just like the usual xy plane grid, then this is one thing you can do. Now notice one thing that this does, unfortunately, is this is a circular paraboloid. It's a symmetrical bowl. It has a radial symmetry that's totally missed by the grid lines and by the fact that I had to do it as a rectangle in u and v, or in other words, is everything that's on this nice symmetrical bowl that's over a square minus 1 to 1 in both coordinates. Well, that's kind of weird, okay? What if I wanted to parameterize it in a way that really reflected that symmetry better? Well, I could do it in kind of a more polar fashion. So I could do here, I could do u times cosine of v. Here, u times sine of v. That's literally just polar coordinates with different names. And then here, I'm going to do just u squared. Enter. Okay. Oh, and now I probably want, I don't really need u to be negative because it's like a radius, but I want v maybe to go from, I'm going to go back to an angle convention like 0 to 2 pi. Ah, now that is much prettier in some ways. I think I want a few more steps in the angle though. There we go. That's nicer, less clunky. Okay. Now that's really a much nicer way in a lot of ways to draw that circular paraboloid. It respects the symmetry better. It's getting exactly, it's cutting it off in a nicer way and doesn't have those 4 weird corner things. And let's suppose we had no idea what this was going to create, and we just started analyzing it again from the u equals constant, v equals constant perspective. If u equals constant, for example, once again like the sphere example, then the z is going to be constant, the radius is going to be constant, and then you've got a, it's going to draw a circle. So if u equals 2, for example, z is going to be 4, and you're going to get 2 cosine v, 2 sine v. Oh, we know what that does. That draws a circle of radius 2. If you set v equals constant, then you're going to get something where the ratio of u and of x and y is always constant, and z is a quadratic function of that. That's going to be one of these parabolas. You see the up and down curves here are parabolas that are, when you project them in x and y, they're just on a certain angle, so a certain ratio of x to y, a certain slope, and then when you look at them sideways, you're getting the fact that z is a quadratic function of that parameter. So you've got, this really does do the parabolas and circles idea much better than that other grid did. So this is a slight example of how the same object can be parametrized in 2 different ways, in a way that one of them might be superior for some purposes. Okay, that's enough for now.